Welcome to the Deep Dive, where we sift through the sources to bring you the most compelling ideas in science. Today, we're plunging into, well, a realm where reality gets a fascinating twist. Just try and picture an electron beam, not as tiny, hard pellets, but something more fluid. It sort of whispers through the intricate lattice of a crystal, and instead of hitting just one spot on a screen, it paints this mesmerizing pattern of rings, like a rhythm, almost music. Definitely not what you'd expect from miniature billiard balls, right? It's really the opening act of quantum weirdness, and it brings us to one of the most, well, audacious, yet elegant ideas in physics. So back in the early 20th century, a brilliant mind, Louis de Broglie, had the courage to voice something pretty revolutionary. We already knew light, traditionally seen as a wave, could sometimes act like a particle. De Broglie looked at that and basically dared to complete the picture. He said, okay, if light can act like matter, then matter must also behave like light. And he boiled this down into one beautiful equation. Lambda equals h over p AP. This wasn't just math games. And hinted that maybe what we thought were solid particles are actually structured motion patterns. Patterns with their own wavelengths, able to diffract, guide, interfere, just like waves. So our mission in this deep dive is kind of twofold. First, we'll unpack de Broglie's groundbreaking idea, really get a feel for its genius. Then we're going to explore how a more modern perspective, which we're calling motion theory, takes his initial insights and offers maybe an even cleaner, more intuitive picture. Get ready to challenge some deeply ingrained quantum beliefs. We'll explore how matter might simply be motion, locking to motion, writing the world in rhythm. Oh, this isn't just about facts. It's about maybe giving you a brand new lens to see reality itself.
Yeah, and it's crucial to see de Broglie wasn't just hand-waving. He was making a very direct connection. His core idea back in 1923, 1924, was that any moving body, anything with momentum p, has this associated wavelength, though, given by phi, that famous equation. And just as vital, its energy E corresponds to a frequency F3. It implies the sort of intrinsic vibration for everything that moves.
So he wasn't saying it's both a wave and a particle like switching hats, more like it inherently has these wave aspects baked in.
Exactly. It's less a duality, more a unified nature. And then he went further with this idea of phase harmony. He proposed that inside every particle in its own rest frame, there's like an internal clock. It ticks at what we call the Compton frequency, SEMC2H. And this internal rhythm, this hidden clock, stays perfectly in sync phase harmony with the particle's external motion as it travels. It's a fundamental synchronization.
An internal clock keeping pace. And that led to his initial pilot idea, didn't it? That a wave guides the particle, which sort of paved the way for the Broglie-Bohm interpretation later on.
Yes, absolutely. That was the seed. And what's really striking is how quickly experiment caught up. Just a few years later, 1927, you had Davison-Germer and G.P. Thompson. They actually showed electrons diffracting, behaving exactly like de Broglie's waves predicted. And later, the same thing was seen with neutrons, whole atoms, even big molecules like C60 buckyballs showing interference.
Okay, hold on. Let's unpack that. It's like saying, I don't know, a bowling ball technically has a wavelength, even if it's so incredibly tiny we could never ever see it. But for electrons, de Broglie's wavelength was, as the sources say, instruments grade real. The universe really had this rhythm. It wasn't just math.
Precisely. These experiments really cemented his theoretical leap. They bridged that gap between wave and particle thinking. But, even with that proof, the standard story often just leaves us with wave-particle duality. Still a bit mysterious, something you just sort of accept.
Right. And this is where motion theory comes in, offering a different angle, suggesting maybe it's not a duality at all, but just one fundamental thing, structured motion.
Right.
It's quite a shift.
It is a big shift. Motion theory asks us to rethink the basics. So space, for instance, isn't just an empty box. It's viewed as unresolved motion. And time isn't some independent river flowing. It's a comparative resolution rate between different systems.
A comparative resolution rate. Okay, that sounds a bit abstract. Can you make that more concrete?
Yeah.
Like an analogy?
Sure. Think of it like this. Imagine you have two really complex, perfectly synchronized gear mechanisms, like intricate clocks. If one suddenly starts running faster or slower relative to the other, our perception of time changing isn't because some external clock governing the universe changed speed. Instead, it's the relative rate at which their internal gears mesh and turn, how they resolve their cycles against each other. That comparison is their temporal relationship. Time becomes this internal rhythm, a sync rate, defining how things phase together, not an external tick-tock.
Ah, okay. That makes more sense. It ties time to the actual dynamics. So if everything is this structured motion, what are particles then? Like electrons or protons? Still tiny points.
No, not points at all. In motion theory, a particle is seen as a phase-locked loop of this structured motion. Picture a tightly wound, self-sustaining whirl of activity, constantly refreshing itself. This loop, this stable rhythm, it actively resists being disturbed or rephased. And that resistance is what we measure as mass. So mass isn't how much stuff is there, but more like resistance to rephase for that locked rhythm.
That's a really different way to think about mass. A particle isn't a point, it's a stable pattern of motion.
Okay.
And the wave function, that thing that often feels like a ghostly probability cloud, how does that fit in?
Right, gets redefined too. In motion theory, it's a phase alignment functional. Think of it maybe as a dynamic alignment ledger, spread out over all the possible ways the motion could configure itself. This ledger doesn't just say where a particle might be found, it actually maps out where coherent, stable synchronization is available in the underlying motion field. So when we calculate 2, we're measuring the availability of stable synchronization, basically where the environment makes it easy for a particle's loop to exist or move smoothly. And the phase part, that stores the ordering tension, like how smoothly different paths align.
Wow, okay. So INTES isn't probability, it's more like a map of stable pathways.
Yeah.
That changes things. So de Broglie's equation, LINUP, what does that become? How does the loop interact with this ledger?
Exactly. Momentum, E, in this view, represents alignment curvature, how tightly the motion is turning or winding through this substrate. The greater the curvature, the shorter the spatial period of that rhythm, which is the de Broglie wavelengths, the things like diffraction. They aren't caused by some fuzzy matter wave. It's ledger interference. The available alignment pathways in the ledger interfere, making certain trajectories much easier or harder for the particle's loop to actually follow.
Fascinating. Okay, let's circle back to de Broglie's phase harmony and those internal clocks. How does motion theory handle that, especially with relativity, which often seems, counterintuitive?
Motion theory actually provides a very natural explanation that internal clock isn't just abstract, it is the loop sync rate. It's how fast that little vortex of structured motion re-resolves itself internally. And the external phase is how that alignment advances along its path. So relativistic effects, like time dilation, they become much clearer. If you change your state of motion relative to something else, you simply change your sync rate. Your internal clock ticks differently relative to the external frame. The phase harmony condition just ensures that the alignment ledger stays consistent across different reference frames. It's about consistent bookkeeping of rhythm, not warping space-time fabric itself.
That feels way more intuitive, changing sync rates. Okay, and does this also clear up that old puzzle about phase velocity sometimes seeming faster than light while group velocity isn't?
Precisely. The group velocity corresponds to the envelope carrying the actual loop, the particle itself. That's what carries energy and information, and it respects the light speed limit. The phase velocity, though, tracks the underlying carrier wave, the abstract alignment bookkeeping. These two speeds don't have to match. A superluminal phase velocity is just non-causal bookkeeping. It's like the pattern of crests moving, not an actual signal breaking the speed limit.
Okay, this really does sound like motion theory isn't just adding ideas, but maybe streamlining things, making puzzling physics more graspable. Does it connect to the bigger quantum framework too?
Yeah.
Like Schrödinger's equation.
Yes, absolutely. Motion theory suggests you can actually derive Schrödinger's equation from de Broglie's phase concepts. If you start with an action principle based on motion, where the cost of moving involves alignment curvature, kinetic energy, and stored misalignment, potential energy, and you minimize that action, you naturally end up with something that looks like Schrödinger's equation. So in this picture, Schrödinger's equation becomes the description of the linearized alignment flow of de Broglie's underlying rhythm, how that structured motion evolves through the alignment ledger.
So Schrödinger's equation just naturally falls out of this rhythm.
Okay.
And what about Bohm's pilot wave idea that sometimes gets dismissed as having hidden variables or being a bit spooky? Does motion theory help there?
It really does. It offers a less spooky interpretation. The pilot in motion theory isn't some separate hidden thing. It's a pilot rhythm, a very real extended alignment structure in the motion substrate. This structure creates easy corridors that guide the particle's loop. And that abstract-seeming quantum potential in Bohm's theory, it's understood here as the curvature cost needed to keep the motion smoothly aligned. No ghosts. Just the dynamics of structured motion.
That makes a lot more sense. A pilot rhythm and non-locality. That weird quantum entanglement thing where particles seem linked across distances, how does that fit?
Yeah, it reframes that too. Non-locality isn't instantaneous messaging between particles. It's more like a shared ledger established when entangled systems are first created. They share a deeply intertwined rhythm or alignment pattern. Then, when a measurement on one part forces a global rephase, like snapping the whole pattern into a specific configuration, the other parts instantly co-resolve according to that shared ledger. It looks like action at a distance, but it's really about the pre-existing correlation in their shared alignment structure being revealed. And yeah, that really makes you question basic assumptions. If non-locality is a shared ledger, it changes how we think about information and causality at the quantum level.
Okay, let's try applying this. How would motion theory explain something like electron diffraction in a crystal?
Right. So the crystal lattice creates periodic areas of alignment resistance. When the electron loops encounter this, their possible paths through the alignment ledger add up constructively where the alignment cost is low. That leads to the distinct Bragg rings we see. The electrons are essentially navigating the paths of least resistance through this structured motion landscape.
Makes sense. And quantum tunneling?
Yeah.
Particles getting through barriers they shouldn't have the energy for?
The barrier isn't seen as a solid wall, but a region that just raises the resistance for the structured motion. But the alignment ledger still allows for a tiny alignment borrow through that high resistance region. The chance of the particle making it through the transmission probability drops off exponentially with how costly that borrow is. It's finding a very high resistance path, not magic.
This is starting to paint a very coherent picture. And those walking droplet experiments you mentioned, the ones on vibrating fluid baths.
Yeah, the hydrodynamic analogs. They're fantastic visual aids. You see a droplet bouncing on the fluid, creating its own wave field around it, and that wave field then guides the droplet's motion. It leads to things that look like quantized orbits, interference patterns, statistical behaviors that mimic quantum mechanics. Now, they aren't perfect quantum analogs. The statistics don't match exactly, but they absolutely demolish the intuition that a guided corpuscle is impossible. They show that this kind of pilot rhythm guidance is actually quite natural.
A real-world example, even if it's an analogy. Okay, let's tackle the big one, measurement. The infamous wave function, collapse. Does de Broglie's wave still just vanish in motion theory?
No, that's a key point. The wave, the alignment ledger, never collapses. Instead, a measurement device like a detector screen acts as a high-gain synchronization amplifier. When the particle's loop interacts with the detector essentially forces a global rephase. It amplifies and locks onto one specific stable pathway or corridor within the alignment ledger, the one that matches the detector state. This rephasing happens incredibly quickly, very decisively. So to our macroscopic view, it looks like a sudden collapse onto one outcome, but it's an interaction, a synchronization.
Ah, okay. So it's not a mysterious disappearance. It's the detector forcing a specific outcome by amplifying one possibility. That makes way more sense. So does motion theory make new testable predictions? What kind of experiment would, really put it to the test, something de Broglie might have liked?
Definitely. One neat idea is a phase index slit experiment. Imagine a standard double slit setup, but you place a special patch over one slit. This patch doesn't block the particles, but it slightly changes the local alignment curvature, maybe like changing the refractive index for light, but for the matter, waves alignment. Motion theory predicts very specific shifts in the interference fringes based purely on this change in alignment curvature. You could compare those shifts directly to what standard optical phase delay models predict. The numbers might be similar, but the reason for the shift, according to MT, is fundamentally tied to the geometry of the underlying motion, not an abstract wave phase.
Interesting. A subtle but fundamental difference in why the pattern shifts. Okay, let's zoom out. If we put de Broglie's original idea, reread through motion theory, next to the standard quantum story, what's the bottom line? What really changes, what stays?
Well, crucially, the predictions for experiments stay the same. Motion theory gives you the right loop soup, the right interference patterns, the right tunneling rates, all of that. The math works out. The huge difference is the why, the underlying picture, the ontology. It's not a duality of waves and particles. It's one single thing, structured motion. And we just observe it in two ways. Either it's spread out extended ledger, which gives interference, or it's localized loop, which gives a particle detection. You get a cleaner story for measurement in forced resolution, not magic collapse.
Yeah.
And relativity fits in more naturally, too. Phase harmony is sync conservation. Time dilation is just loop retiming.
It really does sound like it aims to clear away some of the weirdness, or at least the parts that felt almost mystical. So what common quantum ideas or misconceptions can we maybe finally retire with this perspective?
Okay, first, waves are just probability fog. No, in this view, waves are real alignment structures. Probability comes in when describing how often our macroscopic detectors manage to lock onto a stable pathway. Second, particles are just points. Nope, they're phase-locked loops of structured motion that can localize very tightly when the environment forces them into a narrow corridor.
Okay.
And third, pilot waves mean spooky, hidden variable ghosts. Not necessarily. The pilot rhythm here is seen as a real, physical, extended bookkeeping structure for alignment, not some hidden, faster-than-light messenger.
So Louis de Broglie, in this light, didn't really add mystery to physics. He maybe removed a category error. Matter never stopped being motion. He just revealed its underlying rhythm. And in this motion theory interpretation, that equation isn't some strange quantum rule. It's just what naturally happens when a loop of structured motion interacts with its own alignment landscape. The wave is the ledger showing where it's easy to move. The particle is the loop carrying the beat. De Broglie just gave that beat a name.
Exactly. And maybe we're just seeing that same principle everywhere, from the tiniest electron rings right up to perhaps even our own thoughts. Just motion, locking to motion, writing the world in rhythm.
So, thinking about the world through this lens of structured motion, what new insights might you uncover? Thanks for joining us on this deep dive into the rhythm of reality.